Welcome everybody to our seventh live office hours. We got a couple of great questions today. Most of them are from our user student Bill, who's doing a great job of keeping us busy with questions this semester. So his first question is: you've identified data structures and algorithms as the next logical choice to learn about programming. Besides that, what would you say is the next thing to learn? What do you think?
Ooh, we don't go deeply into object-oriented programming in this course, so I think there's a lot of room to explore that further. And it's a very rich space to develop your skills in. So I would recommend, as an option, looking into object-oriented programming and design patterns as another alternative to data structures and algorithms.
Totally. You could also do something like looking into how web programming works, like learning JavaScript and things like that. It's very similar in sort of the technical aspects to what we're learning here in Python and Java in this class, and you'd be able to apply it to a different domain. So you can do a couple things there. You might also look into, I think, like a databases class might be interesting. That's one place you could go that you wouldn't need a lot of prerequisites to get there. You'd be able to learn some skills to learn how to work with databases, and that marries well with the web programming thing. So there's a couple different paths you can take from this course. For like programming fundamentals, it's all about data structures and algorithms. That gives you practice in programming, and it sort of makes you think at the next higher level. If you want to sort of go wide and learn a bunch of different variety of skills, then you can go and learn some object-oriented programming, and you can learn some web and database management stuff, and kind of get some weird experience.
Right. And if you wanted to go in a direction that was kind of other than a typical academic direction, you might consider something like one of my favorite books is Automate the Boring Stuff, which is a Python book. And it gives you a lot of ideas and examples on how to use Python to automate processes that most knowledge workers encounter in their daily job. Things that you use the computer to do and that take time for you to do. Once you have a little bit of programming knowledge, you can automate those processes and write small programs to do those for you.
Totally.
So that's a good way to gain some additional experience without focusing on a specific course in an academic program.
And I think most of that book is available online.
I believe so, yeah.
Yeah, so you can just Google it and see what kind of examples it gives and things like that. It's super useful. I've used the concepts from that book many times in making my job easier, so I have more time to do the fun stuff rather than the boring stuff. Then the next one is: how important are computer-related math? How important are computer-related maths to understanding and writing programs? Is learning discrete structures and linear algebra absolutely necessary? And Bill goes on to describe how it is a significant time investment. What's your opinion on this one?
I have mixed opinions on this one. I don't want to give anyone like a free pass to not have to learn anything. Math and its various forms are super valuable. It's a set of styles of thinking and problem solving that you gain from math, and perspectives and ability to solve problems across a wide area of domains. And that's especially true in computer programming. So is it possible to do significant computer programming without diving deeply into those maths? Yeah, and a lot of people do. But having those math skills opens a lot of doors and gives you a lot of patterns that you can apply in your computer problem solving that, if you didn't have those math skills, would be things that you would not be able to even imagine.
Yeah. And I totally agree. I think it's so in my field of sort of computer engineering and embedded systems and stuff like that, the math part is really significant. right? Because I'm dealing with sensor information, I'm processing a lot of raw data, I'm doing things like trying to make meaning out of raw numbers and stuff like that, that then I can write programs to act on. And that involves a lot of mathematics, it involves a lot of calculus, sometimes, well, not a lot of calculus actually, but it involves a lot of algebra, and it involves a lot of trig, and it involves a lot of like differential equations sometimes, and stuff like that. And without those tools, I would not be able to do some really incredible things. Or if I was trying to do them, I would have way more difficulty getting to a solution that's workable. I would have to write thousands of lines of code rather than a few math equations in my code that then do a lot of the work for me, right? But I don't see, there's a lot of domains where you don't need that information to succeed. But like Phil was saying, it opens a lot of doors. So it's kind of up to you and where you want to end up. And a bunch of very wide variety of different disciplines have different needs and things like that. If you're going into sort of like business software development, or sort of generic software engineering or web development or anything like that, you're probably not going to use the really high level math. Having a facility with algebra and trig is really helpful, but super high level math is not going to come around to you. However, if you want to go into like machine learning or data science, or if you want to go into embedded systems, or if you want to even do stuff like programming for game development or anything like that, those are incredibly math heavy disciplines, and they're super exciting, and there's a lot of jobs in them, but you have a sort of knowledge chain that you have to get to be able to execute those.
Yep.
Yeah.
So this next question is stated simply, but it's a big question. How is information stored in the cloud? Does it have a physical on-off switch somewhere to exist? So let's take the second half of that first. Information that's stored in the cloud, is there a physical representation of it? Is it transistors and ones and zeros physically embodied in some way? Yes.
Yes.
We can't have disembodied information. It has to exist in some physical form. What is that physical form when we're talking about cloud storage? So I have a Google Drive account. I have a Dropbox account. That's all cloud storage. The information on my Android phone is all backed up to a cloud service. What we really mean by cloud storage is non-local storage, right? So the physical information is stored on someone else's physical devices, whether those are servers running an Amazon service. There's computers somewhere, most likely with spinning hard drives that have the information encoded magnetically on it. I think a lot of those spinning hard drives are being rapidly replaced by solid state drive, flash drives.
Yeah.
So no moving parts. And that's probably what, 85% of the information that's out there these days?
Yeah, totally.
Maybe more.
Yeah, and the basic idea here is that the cloud is not like a magical thing. It is just an application of computers, and any information that is either stored or transferred has to go. It's a 1 or a 0 in voltage or some other representation of a physical phenomena, right? So you don't have, like, we think of the cloud as just the other end of the internet. It's a pipe that opens up somewhere, and that's where all of our data is stored. But that pipe, though, the internet, the physical connection, goes to another server, another specialized computer somewhere in a massive warehouse, either run by Google or Amazon any of these. Most of these, those are the two big ones, right? And there's a bunch of other, like Dropbox and places like that, all have services like this. But it's just a giant warehouse full of computers, and they've all got they all have storage, and that's where your data lives. And you should look up pictures of these warehouses on the internet. They are massive. They are incredibly huge, and you would be blown away by the scale of data being stored. And that's physically where it is in a lot of places. And this is interesting because companies get nervous about having their data next to somebody else's data in these facilities, right? So for us, if you have a Google Drive account, or even if you have a Google Mail account, your data is stored with everybody else's data on some servers somewhere in the world, typically close to wherever you live. But if you're a company, and say you're someplace like Boeing or General Dynamics, where you've got really sensitive data, you've got trade secrets and stuff like that, you don't want to be sort of in the same place, even physically, from everybody else's data. It's a security concern. So you can pay for a dedicated server that's just yours. We've got one box that's just yours alone in Google's warehouse or in Amazon's warehouse or whatever. That's you get a personal cloud sort of connection, sort of thing.
Yeah. Conceptually, cloud storage is not any different than local storage.
Right.
So when you access information on your computer that's on your hard drive, there is a communication channel between the hard drive and the CPU.
Yeah.
And that communication channel is used to transmit data back and forth between the hard drive. With cloud storage, that communication channel is the internet.
Right.
Right. So
yeah,
conceptually, it's the same kind of thing. The advantage that we get from the connection medium being the internet is anywhere the internet is available, theoretically, you have access to your cloud data.
Right.
Whereas if it's local storage, then only if you have local access to that device do you have access to that data.
Right.
So there's the big sell for cloud storage.
Totally.
I'm sold. When it first came out, I was all like, there's no way I'm going to let my information be wherever that is.
Right. Totally.
Now I'm addicted to it because
Yeah.
my information is wherever the internet is.
Right.
So
Yeah.
I don't, if I forgot to bring my laptop with me, that's okay. I could just log in and get my information.
Totally. And anywhere, right? And
Yes.
I was kind of the same way. I was a little more trusting probably right off the bat, but I didn't start using like cloud services really seriously until probably 10 years ago, something like that. Now I'm like, everything I have is is stored somewhere else, because I've lost so much data over the years, over my lifetime, that I wish I could get back sometimes. And having it stored in multiple locations keeps me from losing anything ever again. So hopefully, at least, cross your fingers.
Okay, this next question is about arrays. Are arrays mostly used to simplify tedious processes with large amounts of data, like object-oriented programming on a bigger, simpler scale?
I don't know if I'd say simpler, but the general idea is totally there, right? The whole idea about arrays is that you have a way to store and organize large amounts of data in local memory. Right. So now rather than just one variable, one copy of a thing under one name, we have as many as we want, as long as we can fit it in memory, and we can now index them with a number rather than having to use just the name. So we get a name number combination rather than just the name. And now we can do all kinds of stuff with that, depending on how we figure out how to generate that index, where do we put things in that array, and all kinds of stuff like that. So it is primarily about organizing really large amounts of data.
Right. The first question that we discussed today brought up the idea of data structures. And an array is probably the simplest example of a data structure that has some structure to it. There's some compositeness to it. Before we got to arrays, all of our data was stored in variables, and a variable stores a piece of information, an integer or a float or a string. Arrays store a collection of data, a collection of information. So it's the first structured example of data that we come across. And it is probably the simplest example of a data structure. It's got some interesting limitations. So all of the data in the array is of the same type. So maybe it's a collection of integers, or it's a collection of floats, or it's a collection of strings, or it could be a collection of cats if we wanted to. But the important part is that it's a collection of same things. So it has that limitation. The way they're structured in the computer's memory is all of the elements of an array are located contiguously in the computer's memory. And this is not an easy thing to achieve because a lot of multitasking systems like modern operating systems are using different pieces of memory at different times. So finding a big chunk of contiguous memory that's not being... What's this about?
You were probably looking at your work stuff.
Oh.
That looks like yeah.
So okay, it's okay.
Yeah, okay, it's okay. That's not our broadcast.
I had some weird thing pop up on my screen. Sorry. It's not an easy thing to achieve, but we get a big advantage for that. And the advantage that we get for that is, since all of those pieces of information are the same type, then they're all the same size. And since they're all located contiguously in memory, if we know where the first one is, it's a simple mathematical process to find any one we want. Because if we want the fifth one, it's just the location of the first one plus 5 times the size.
Mm-hmm.
And that tells us. So we get a lot of efficiency in terms of access to the elements of an array. And so that's where the value of that comes from. And if you start talking about object-oriented programming, objects are another type of data structure. And the biggest difference between objects and arrays in terms of data structure is an array is a collection of pieces of data that are all the same type. An object can be a collection of data, the pieces of which can be different types. So I can have a string and an int and a float as a part of that structure, which is maybe a student and their age and final grade or something like that.
Yeah, totally. Okay, and the last question is something we get asked a lot, and it's a really hard question to answer. So, do we have any further recommendations on where we can go to learn more? There's so many options, and it's really hard to determine what's worth your time. That is a really hard question to answer because it's in my mind, it relates mostly to what you're interested in, right? We talked about a bunch of different sort of paths, and there are so many different paths and specializations in programming and learning how to do engineering and stuff like that. I would take sort of an inventory of what you like to do, what you find interesting, and how that intersects with what you would like to do, where you want to go, and kind of look at that intersection, right? You want to. What I'm trying to say is that the path will be clearer if you sort of inspect your own motivations and passions and line up what you're good at with what you're interested in. If you can find something where both of those things match, then pursue that with all of your energy. But specific classes or specific other resources are a little more challenging because there's so many of them out there, just like you mentioned.
Yeah, it's hard to recommend specifics for a class full of students. If we sat down with 1 or 2 people and they could express like what they're interested in, as you're saying, we might be able to offer some specific recommendations. So instead of that, all we're able to say is things like there are a lot of great books out there. I still go to bookstores and look at the shelves, and I'll grab 5 or 6 programming books off the shelf, get a cup of coffee and sit down and read those for a couple hours, and then usually walk out of there with 1 or 2 that I really fell in love with. There are a lot of great websites that do either tutorials or challenges. And I'm a big fan of challenges. If what you're wanting to do is to kind of continue building your skills, a good way to do that is to engage in these programming challenges. A classic one out there is a website called Project Euler, EULER. There's codingbat.com, which is a bunch of little challenges that you can try, and it gives you feedback on that, and they support a number of different programming languages. There's coding challenges for Python out there. If you wanted to get more connected to the industry and people who are practicing, there are local user groups. So you could find a local user group for Python or a local user group for Java, find out when they meet, go to their meetings, talk to people, get some ideas from them. It's always a good idea to kind of connect with some actual people rather than just books and websites.
Totally.
So there's
in the same vein, there's like those sorts of organizations are probably going to be putting on hackathons, really short duration challenges. You can either participate often as an individual or a small team, and you can sort of develop your skills and learn from each other that way. Most of the time they have challenges that are for all skill levels, everybody from introductory up to professional and expert, and you can find something that will challenge you, but you'll learn a lot in the process. If you want to go like the hardware route, this question again comes from Bill, and he goes on to talk about how he's using what he's learned in the class to do computer-aided drafting and computer numerically controlled machining systems, and how he sort of upgraded his job with that, which is awesome. Congratulations again, Bill. If you want to learn more about how you can work with hardware and program hardware, I suggest getting it's called an Arduino, 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 and it's a little tiny microcontroller board, and it's got a real simple programming interface, and you can make lights blink, and you can do you can control physical hardware, control motors and lights and all kinds of stuff with it, and it's a really, really powerful tool and super exciting. I think they're super fun. So you can do that. A little more sophisticated is stuff like a Raspberry Pi. That one is probably about the same price. It's more powerful, but it takes more extra hardware and knowledge to sort of work with. But it runs Python right out of the box, which is super cool. And you can go to work there. Both of these have great communities where you can talk to other people about what projects they're working on, see examples, and learn a whole lot about how the hardware, the underlying hardware works, and what you can do to control physical systems and machines in the real world, which is super neat type of stuff. Yeah. Okay. Jill says we are no longer. Jill says to Phil, we are no longer friends.
What did I say?
I don't know. I don't know what you said.
That was not my intention.
Yeah. Yeah, something like that. But yeah, it doesn't look like there's many people watching currently. So we are going to have one more of these live sessions. It's going to be during the math comment. So we're going to have one more of these live sessions. It'll be during the finals week. It'll be on the Tuesday of the finals week. So if you have some questions about the final or how you to prepare for it, we'll have a discussion open for that. If you want to ask questions there before you take the exam, please ask any questions there, or if you have any questions about the class or anything like that, we'll see you guys in the discussion boards.